准备开始上课。讲一下我们现在好像有点超前进度了，我们大概今天会把 MFCD 讲完，我们大概快了一堂课的时间，就快1点半课吧。那我们就跟我原本预计的也差不多了。我每年都好像会发现这边部分我们规划太久时间了，大概但后面 ASR 其实确实会花比较多时间啊，大概会提早开始做 ASR 相关的分析。那如果我们真的就把典型的 ASR 上完的话，那我这边我就会把现在 still 聊的 ASR 做个简单的描述给大家知道。那如果时间不够啊，因为现在都跟 still 走了，所以可能就停在经典的 ASR 这样子。OK，大概先跟大家讲一下这个过程。OK，好。不过 midterm 到时候是4月底的事情，OK，那大概只会 cover 到，就是会 cover 到 cash flow analysis 这一段而已，就是这一段而已。那后面那个 ASR 部分，的一些模型，大概是会在 final 时候才会进入到考试里面。OK，先跟大家讲一下。Alright, so let's continue on to the cash flow analysis. So I think we've come a long way. Okay, I started with speech production, understanding linear prediction, various tools of time and frequency domain processing, and cash flow analysis and other mathematical operations that help us tease apart two things that are called convolution. Okay, one is more of a low frequency kind of messaging kind of thing, and with the high frequency thing, you can sort of separate them apart. The source for the production. And then later we started writing features, right? LPCC, doing linear prediction analysis combined with cash flow analysis. We can write features that represent a particular frame of speech signal that well captures the most important information within it. So as we move from the production to the perception, okay. Now to talk about perception, we started about here, right? So let's know a little bit about a basic sort of level of our human hearing mechanism. The anatomy of our hearing is our ear, so it involves basically three components. The outer ear, the middle ear, and the cochlear. Okay, the outer ears are basically a sense of, it's basically this kind of structure. The structure will collect these standing waveforms that travels across the air. They collect them and you see it starts to oscillate, right? In the ear canal that's within your ear. And the middle ear bones that provides a resonance, okay, and because it's like one of the instruments, right? If you go to it and then you start to resonate, it's gonna resonate at a certain frequency, try to boost up a good efficient transfer of a certain range of frequency within your standing waveform. And that standing waveform will go into a cochlear, and that's where the bandpass filter operation that happens physically in our ear, so that it transmits neural activities into your brain, and then your brain take care of the rest. Okay, so you can kind of like imagine our ear, and then within this cochlear processing, it's like if you're more familiar with the terminology like feature extraction, this is basically a feature extraction, right? It's gonna represent a wave of speech sound bouncing to the thing according to its frequency components, and it's gonna firing the neural activity according to the frequency component that our ear responded to. Okay, and then it's sent to our brain, where our brain take care of the rest of the interpretations and so on and so forth. Okay, it's like this is on the side note, right? It's like your eyes, right? Your eyes, some of the neural activities in your eyes, it does a front end processing of this kind of convolutions ideas in the eyes, where then it sends these electrical signals to the back of your brain to interpret what you're seeing as this particular object or that object, this person, that person. Those interpretation happens in your brain, but your sensory inputs actually processes like a feature extractor to extract certain important information that your brain cares, and send it to your brain. Okay? So think about that. Quite amazing how our sensory system provides that kind of a front end processing that our brain requires to do all the high level understanding the signals that it perceives. Okay. So our ears involves all these components. Okay, middle ear to the three, obviously provides a impedance matching to the inner ears, so that it ensures efficient transfer between 500 to 4,000 hertz. Okay, again, This is by evolution, right? So because we know humans, our speech, a lot of the contents can concentrate around this particular hertz, so that as you evolve our human, make sure we have set of right organs within our ears. They make sure this part don't miss it. Okay, so it actually sends to your central inner ear. The inner ears where the most complex things happen is a fluid-filled chamber reached by the basal membrane, and then integrated with the auditory nerves. Okay, basal membrane is characterized by a set of frequency response at different points along the membrane, what we call them Bengal filters. So later on, if you hear speech processors, they talk about filter banks. It's basically the ideas really comes from our understanding of our hearing hair cells. So inner hair cells distributed along this basal membrane convert mechanical motions to neural activities. About 30,000 neural nerve fibers link nerve hair cells through auditory nerves. The hair cells are the things that as you get old, this thing dies down. Okay, so usually you start, the higher frequency hair cells start to die. Okay, then because those starts dying, even if your membrane do activate, okay, it doesn't change, it doesn't interact with this hair cell. It doesn't interact with the hair cell, like it doesn't bend, it doesn't trigger the neural activity. You no longer hear those frequencies. Okay, that's where we start to have hearing loss. Okay, so there are sets of medical devices that actually tries to replicate this thing. Even if your inner hair cell dies, it can implement some device in your ear. It actually direct triggers the nerves, okay, at those locations, or without going through the hair cell. Then you can actually hear back some of the things that you do normally hear before losing your hearing. Okay, so understanding this mechanism, there are many sets of technology that actually people developed for those hearing loss populations. But anyway, so that. So about 3,500 hair cells, 40 hairs per cell, about 20 neurons per hair. Again, this encode essentially frequency component. Okay. They are actually in this sort of a shape. Okay, but let's flatten them, make them into a line. You basically see, depending on the stiffness of this basal membrane, it actually will respond differently to different hertz within your signal. Okay, so at the higher frequency, this part will start to, mechanical motion, right? This will move. Okay, then it moves and then it touches all the hair cells around it, and those hair cells get bent, and then it touches the neural auditory nerve. And then once it touches, it's like electrical circuit. Once it touches, it connects. It connects and sends voltage, send the electrical signal to your brain. Okay, and then so how we know which frequency responded to, because it's basically a physical organ. So the stiffness, the width of these things are different. So that's why it'll respond to a different frequency within the signal that you hear. Okay, so it's a carefully designed physical organs in our ear that actually work like a bandpass filter. So understand that basic understanding of hearing, we start to try to extrapolate from an engineering perspective. Okay, so transductions are acoustic signal to neural nerves. Okay, so the mass and the stiffness of a basal membrane varies along the length of the column here. Okay, so each location XY along the basal membrane tuned to a particular specific frequency. Again, it vibrates with high amplitude. Frequency response amplitude modeled by a bank of bandpass filter. So vibration of location at location XI, HIOT is can look at it as like impulse response of a bandpass filter. So it gets you moves in particular one directions. Okay. Then the vibration of basal membrane transduced by bending of the hair cell. Hair cell detect motion of the membrane in one direction, so called half-wave rectification. So again, it moves and then it bends the hair cell, and then once it bends, it intervenes with the auditory nerves and then it sends signals. Okay, so based on the hair cell intervening with the peripheral auditory nerves, they tend to fire quite a bit when this hair cell bends. Okay. So the average firing rate of the nerves at location XI along the cavity, we can write them as RTWI, Firing rate increases monotonically, but not linear with the amplitude of the hair cell bending. The more it bends, okay, the firing rate increases monotonically, but not linearly. Okay, so you think about this, right? You have a physical organ that's gonna move, right? And the movement of the amplitude corresponds to the frequency within your signal. As there's a high energy signal within a particular frequency, meaning it creates a high amplitude variation of your membrane, and that high amplitude of variation in the membrane creates a high bending of the hair cell. The more it bends, the more it fires. The more it fires, actually it sounds loud. Okay, so basically that's kind of the overall sort of a streamlined approach of how the human ear processes. Okay, so the firing rate approximately follows the follow law of your actual bending of the hair cell. Okay, understand this idea. So we wanna introduce the concept of perceptual frequency scale. Okay, this is important. The usual frequency scale we know when we perform Fourier analysis, that's called linear scale. Okay, it corresponds to the actual frequency, okay, one-to-one linearly, okay, to the thing that's in the signal. Okay, so there's a derivation of we call it perceptual frequency scale. It's basically a scale on the frequency more correspond to how we human would perceive the pitch or the frequency within a signal. It's not the same thing as the frequency in the signal. What it is how we human would think the frequency is in the signal. So basically think about this little bit concept drift here. So there's a scale, there's a frequency scale on basically purely objective from the signal you can compute that's derived come from Fourier analysis, looking at sampling rate, you can actually know the actual frequency of the signal. The perceptual frequency scale means how we human think. Okay, when we hear it, what would you think that the frequency is? Okay, so they are not equivalent, okay, right? Because it depends on the specificity of our human sort of ears in terms of processing those bandpass filter effect. So we don't respond in no way in the cochlear this specimen, they don't respond linearly, okay, to the frequency in the signal. Okay, we respond monotonically but not linearly, okay, to the frequency scale. So the way we're sensitive to the changes in the frequency scale are not equal across all the frequency that's in the signal. So that's a reason that there's need to be a perceptual called perceptual frequency scale. So the idea is you use the center frequency of the cochlear to perform speech analysis. So we perform frequency analysis not directly looking at the frequency linearly in the signal. It's looking at how our cochlear, if we break them into bank of bandpass filter, what are their center frequencies, and utilize those center frequency as a frequency point to analyze what happens in the signal. Because you can imagine, because our cochlear is a bandpass filter. Looking at those center frequency of those bandpass filter, it will closely resemble how we human really try to bandpass those signals in our brain. Okay, right? So that's the basic motivation of why perceptual frequency scale is important. Okay, there are two scales. One the one of the famous scale called bar scale. It's a critical band scale. Its idea again tag along all this, sound coming in, provide impedance going to the basal membrane, create firing rate, and then there's neural activities. Okay, so you have an acoustic signal that sounds of two pure tone, like two frequencies. If the two frequencies get very close, right, then they're within the XI, that regions of the membrane. Okay, so it's going to be processed by the same filter. Okay, once being processed by the same filter, we know the firing rate is approximately monotonically to the amplitude of the original signal's frequency, right? So basically, some versions of A1 plus A2 to the power law. Okay, if F1 and F2, if these two signal, their frequencies are actually far apart enough, so that means you have your basal membrane at two different locations where it shows amplitude goes up. Okay, so the total firing rate at these two locations will be a summation at two different bandpass filters. So okay, each one of them will be correlated to their individual amplitude. This summation is going to be greater than this summation. Okay. So what that means, when this summation is greater than summation, there's more firing rate. Okay. here than this. When there's more firing rate, more neural activities, that usually also means, okay, it's louder in your ear. So it's not the energy within the signal that makes you think it is louder, okay? It is actually your auditory nerves, how much it fires, makes you think how loud that noise is, okay? That speed sound. So keep this clear, okay? Loudness is a perceptual number, okay? Energy is a signal number, okay? They are correlated, but they are not one-to-one. The way you think a particular sound is very loud, okay? It depends on this firing rate, okay? The firing rate of your auditory nerve to your brain. That's how your brain processes a signal and think, this is a loud signal. Okay? And then when your signal has two frequencies that's very close to each other, they're gonna be operated by the same bandpass filter. And that bandpass filter creates an amplitude mechanical motions, right? That mechanical motions bands creates firing rate. Or if you have the two signals that are far apart, becomes two bandpass filter, each one of them bends. Each one then creates individual firing rate. This will be bigger than this number. So again, if you think about this signal, right? You compute this energy, okay, with different F1 and F2, they are the same. But because F1 and F2, the distance between them become different, your brain will think one signal is louder than the other signal, although their energy is exactly the same. Okay, that's a trick, That why we really want to understand how a human perceives the speech sound condition to the frequency within that speech sound. Okay, so I want to make this point clear. That there's a reason that we actually want to study the speech perception skill. And then if you recall in the very first class, you always want to have this picture in your mind, speech production. The way we utilize our lung articulators move so that we have sound, which is a set of waveforms generated, okay? And then the waveform is going to be recorded with this is a speech signal, okay? This is speech sound, speech signal, and then there's a human ear collecting those sound, becomes a perceptual speech signal. So there's a produced speech signal, the recorded speech signal, and then perceived speech signal, okay? These three things are different. Okay, so just keep that in mind. Okay, this, and then when we engineer what we process the recorded speech signal. Okay, where you can imagine this microphone is like another ear, right? That it creates another sort of perceptual effect within its own region. Okay, but we have two human speech production, human speech perception devices, speech recording. So again, keep this in mind. Here, what we're talking about is human perception. I understand human perception from the perceptual scale. And then Bark scale. Okay, let's talk about Bark scale. So Bark scale, we basically, instead of saying frequency 100 Hertz, 200 Hertz, 300, we say, okay, Bark scale 1 to 24. Okay, each number corresponding to a center frequency, color frequency, and actual band, because it's band passing, right? So we got a critical band. When two signals are within the critical band, they'll be processed by the same Bark filter. Okay, then within them they will sound equally loud. Okay, so to be able to determine the Bark cell is basically we try to find the distance between F1 and F2 at which the sound starts to the speech sound or the sound starts to sound louder. And this particular F1 F2 difference we call the critical bandwidth. So, and this kind of frequency scale given by the critical bandwidth, we call it Bark scale. So, understand that we're deriving a perceptual scale. Okay, every scale, right? A number increases, that means things have changed. Okay, in linear scale, that means a hertz has increases 1. Okay, here what it means is if you include if you increment your scale number to another number, it means the signal that's being that have the distance is the frequency distance between the signals. If they have multiple frequencies in that signal, is distance enough apart so that they start to sound different. So I mean being processed by two different critical band pass filter. Okay, so that's what we call a Bark signal. You can see the bandwidth. Okay, they don't linearly increases. Okay, it also means that critical bandwidth as it gets to a higher frequency, it gets wider. Okay, so that means what? You know, if you look at here, right? That means there are a lot of frequency. Okay, that's going to be processed by the same bandpass filter here compared to here, right? There are only 100 hertz. Okay, that will be processed by the same bandpass filter, the same location of your Bezier membrane. In here, there are about 3,500 hertz of frequency that can be processed by the same thing. Okay, so again, know that our human ears, if you look at this, another thing you can read off is our human ears are definitely more sensitive to the lower frequency component versus the higher frequency component because your cochlear membrane, those lower frequency component moves a lot more, even if there are small differences between the frequency values in your signal. As it goes to higher frequency signal, not a lot of them will move a lot. Okay, so the range of frequency essentially will all correspond to a single location of their Bezier membrane. Okay, so that's how our human ear processing, which also makes sense. Okay, again, this is all evolution. Okay, most of our speech, most of our information content that we use to survive in this world located in lower frequency. So there's no point to put a lot of effort in actually resolve high frequency component if you don't need it for your survival. So a lot of our perceptual mechanism actually works quite well for low frequency, but not as much for high frequency. Talk about male scale later. Because of this, we can actually draw different. We also draw different curves. So this is an equal loudness contour. Okay. Here's the sound pressure level. So actually, we call the recorded speech signals actual pressure, right? So this is the y-axis is the actual speech signal. The pressures are actually shooting out from your mouth. Okay, the amount of effort, me speaking. Okay, right. So that if I speak with a high effort, that means I have a high pressure out of my mouth. Okay, this is pressure. And the frequency conflict with the signal that actually just generated all these speech sound that you hear things that are being resonated. Okay, there's some frequency and then this contour means along this contour, this particular frequency with this kind of effort in speaking, they will result in the same loudness for a human to hear. Okay, so 500 hertz. Okay, about 5 or 10 dB will sound the same loudness as you speak about 100 hertz, but almost 30 dB. Okay, for a human to listen to these two sounds, they'll think they sound equally loud. They create the same approximate firing rate, auditory nerves that do think these two signals are equally loud. So again, let's make sure this mindset is clear. Loudness is perceptual. Sound pressure, this is speech production. Okay, the way you produce. This is what's involved in the speech signal, the frequency content. Okay, all these three things, sort of intertwine and then creates how loud you think what happens in various frequencies. Okay, so keep this in mind. The loudness depends on frequency, depends on intensity, depends on energy. How do we know? Okay, usually they're very experimentally determined. Okay, meaning they recruit humans, come in, play particular tone with particular pressures, let them hear, tell me when you think they are the same loudness or no. We do a large scale human subject study and then draw these curves. Okay. So perceptual study, a lot of them involves basically recruit a lot of people and ask them about their opinions and then try to formulate these curves. Okay, so very empirical experimental design. Okay, but very useful. And then I think it's an important concept to keep in mind. Production, perception, and the recorded speech signal. We don't treat them as the same signal. They are three different things. Okay, and then when you have a particular terminology to describe the speech signal, making sure whether you're describing them from the speech production, recorded speech signal, or human perception. Okay, so these will be three different things. Okay, so hopefully after this class you will know, how loud you're speaking depends on who's listening to it and depends on the frequency involved. Okay, of course it does sort of also depends on how much effort you speak that, but not totally. Okay, just keep this in mind. Okay, so along this Bayesian membrane location, we can also experimentally determine the relationship between the Xi and the Bayesian membrane and then the filter bank center frequency. Okay, so we can look at the response of the Bayesian membrane to sinusoids of a different frequency. Okay. Again, all these things are experimentally designed. Okay, the frequency spacing of one part is approximately 1.2 millimeters along the Bayesian membrane. Clear total length is about 32 millimeters, approximately that would be 26 filter, like a 26 filter responses to the speech signal. Again, all these are approximate. Okay, everybody is a little bit different. Okay, so you may be 1.12, the other person is 1.21. Okay, maybe you have 33 milliseconds, I have 30 milliseconds. It depends, and then all these things are continuous. Okay, so we kind of just approximate because we're looking at sort of this kind of overall. This is how engineering mindset works, right? Making things that are originally continuous and then discretize them. So say, okay, there are 26 bandpass filters. Okay, so we can operate like 26 filters. Okay. But in reality, if you look at it, this plot that we show, this is the cast here, right? So even at a very high frequency, right, it doesn't mean that it doesn't respond, doesn't provide a response to the low frequency component. It's just low energy, okay, low response, okay, but still you provide high response here. So the whole thing moves, okay, but we extrapolate to say that okay. Here's a bandpass filter, here's another bandpass filter, here's another bandpass filter. But in reality, the human ears are more complex. Even the high frequency part of the neovascular membrane also has response. It also still has this amplitude response, right? This is say 500 hertz. Okay, this is the highest point, like a 10,000 hertz bandpass, a center frequency bandpass filter. It still has response in here. Okay, so it's not when you have that bandpass, it's not discrete only really to this region, but it's approximate to that region. Well, another thing you can see that is filter tail drops more slowly toward the negative, meaning the low frequency part versus the high frequency part. So again, it's pretty opposite. So the slope here versus the slope here, okay, here drops more. Okay, here drops slower. So you have a more we call a low frequency will take over high frequency things because of this shape of the filter. They're not actually symmetric. Okay. Later we'll see as we derive MFCC filters, we assume it's symmetric, but in reality, real life animals, we don't respond that symmetrically. And then again, you think about the evolution tells us it cannot be that, right? Because the evolution tells us you have to pay a little more focus to the low frequency, because the low frequency content within the signal has more useful information for survival. Okay, so across all species. So your internally or a lot of your sort of biological underpinning will actually make sure you always have this mechanism that responded to low frequency, not high frequency. Okay, so again, this is okay. So understanding that, let's come back to the final MFCC we'll talk about. So now we know a little bit about the on-train models, how we human do hearings, okay, all these fine range nerves, and then we understand that the ideal perceptual scale is how we human process frequency within the signal so that it sounds different. Okay. Now remember LPCC, now we can move on to we call MFCC computations. MFCC is probably the most well-known acoustic features that exist for speech technology, like ever. Okay, so it's been there for used for at least 20 to 30 years without people finding any better features. Okay, until nowadays where you have a large amount of data, then you start using deep neural network to basically to reduce the idea of doing MFCC. But prior to this age, right, I think at least 30 years, okay, nobody has found a better features to represent speech signal for speech technology better than MFCC. Okay, so we're not counting MFCC. So MFCC really here is motivated by the psychoacoustic theory of human perceptions. Okay, and then repeat human listeners, we don't perceive pitch in a linear way. Perceptual scale of the pitch judged by the, so we need to find another perceptual scale. That's not the linear scale. And then again, judged by the listener to be equal distance from one another. So that means we'll play different tones, okay? Right. So again, if I play 100 and 200 hertz, okay, this is 100 hertz difference, okay. I will find another signal that you think the difference will be the same as that 100 hertz, okay. But it may not be 100 hertz because as you go into the higher frequency, okay, it takes a larger difference before you hear the difference, okay, right? So that's how we human process. So we don't respond linearly to frequency differences. That's how we're saying. And then Mel scale, right? MMCC, the Mel scale, okay, it's a way that we're trying to find how we respond equally to the differences. Okay, so in the Mel scale, every point differences, all human perceive that is an equal differences. Okay, but in reality, when you convert that back to a linear scale, it actually gets wider and wider in the high frequency. Okay, so keep this in mind. So Mel is a unit of measured perceived pitch. Okay, usually by definition is a 1,000 hertz to 1,000 Mel. Again, by experimentation, perception can figure out the relationship between the physical frequency of the tone and its perceived value. Engineering approximation. Okay, there are two ways people approximate, basically change back and forth between linear scale and the Mel scale. Approximation 1 is a linear relationship between Mel and hertz between 1 kilohertz. So 1 to 1, okay, 100 hertz equals 100 Mel, 200 hertz equals 200 Mel, 201 equals 201 Mel. Okay. Prior to the below 1000 hertz, they are equal, okay. But then after 1 kilohertz, they are log relationship. Or you can write them as a single formula, okay, F Mel equals to 1000 divided by log 1 plus F divided by 1000. Okay, so in a single formula, you actually can do the same thing. Okay. So in there, so what we usually do is change the linear scale into Mel scale so that we can derive proper features. Okay. Again, to be able to compute the right representations of the thing within the signal, and then you can compute whatever you like. Okay. Okay, and then another idea here, critical band, same thing as the Borg scale, right? Perception of a tone depends on the energy in the critical band or bank of frequency around that omega naught. Okay, so the bandpass effect is about 100 hertz for your tone that's less than 1 kilohertz, and then log increases for that's greater than 1 kilohertz. Okay, so the perception of a particular tone that we know already in Borg scale, like if they're getting very close, right, it sounds less loud than compared to have two tones at two different positions. Okay. So the way I can perceive how the particular pitch or particular frequency within a signal depends on the bandpass effect. Okay, the energy within that bandpass effect of the filter that I'm processing it. Okay, so again, repeat. Mel scale is a scale, right? You know, it's a scale that represents equal differences that we human can hear. Okay, linear scale doesn't care about how you human can tell difference or not. It's a mathematical operation. You include like 1000 hertz to 1001 hertz. There's one difference, but that one difference is that perceptible in our human brain. It may not be perceptible. So we want to find a scale that every difference is equal differences in a scale. That's called a Mel scale. Okay, so and that's a perceptual scale. So the way you hear the difference, if I add another value to that scale, you hear the same difference. Okay, that's called perceptual Mel scale. Okay, and once you have perceptual Mel scale, another terminology you want to include here is within each of the bandpass effect of that tone of the frequency. It's going to depend on basically the bandpass effect of the bandpass filter, because it's a bandpass effect, right? If you imagine this, this cat's response, right? A frequency interference here. If you have a tone here, as it goes through this bandpass filter, it's gonna be modulated by this effect, not the peak part. It's this part, right? So again, we want to look at how around this critical band
how much energy is going to let that frequency through. Okay, so that critical bandpass supply you also need to take into account. So in ASRO engineering, what we do is use the total energy in a critical band around the center frequency to be able to represent what's happening at those bandpass filter. Okay. Then once we have all these different points, okay, then we can compute the Castro analysis, okay, on those different values, then finally derive the pH. Okay, let's think about this. So the practical implementations of MEL filter bank. So we imagine our bandpass filter are like a set of triangle filters. Okay, triangle filters. So you can design 26, 30, or whatever you like. Okay, usually it's 26, sometimes 40, sometimes 30. Okay, why is that number? Again, the number because of our understanding of the basal membrane, the total length is about 30 milliseconds. We know approximately critical bandwidth sits around 1 millisecond. And that's usually then we split the entire frequency axis into 26 to 30 to even 40 points. Okay. So what we do is need to design this equal bandwidth and equal spacing triangle filter. Okay. But if you write them and represent them in linear scale, that means as frequency goes to higher frequency, the bandwidth gets larger. The differences between the center frequency gets larger. Okay, but within less than 1,000 hertz, they are almost equivalent. Okay, right? So it's linearly proportional less than 1K hertz. But after 1K hertz, okay, it starts to become sort of a log relationship. Okay, but in MEL scale, okay, they are equal bandwidth. So let's design a triangle filter. Then 26 of them. Okay, let's split the entire frequency axis. Okay, all of them. If it's every MEL scale. Okay, so if at 26, then every in MEL scale they always have the same difference in the center frequency in terms of MEL scale. They always have the same bandwidth. Okay, in the MEL scale across all these 26 filters. That makes the design of this filter easy. Okay, then we can turn them back into a linear filter that you look like them is basically they're more tightly distributed within 0 to 1 kHz and then more widely distributed over 1 to 4 kHz. And once you have this triangle filter, right, the speed signal to an FFT having this triangle filter, and when it adds up the energy output from this triangle filter, then you have each one of these will have a number. Okay, then we take log of this thing, then do Castro analysis. So that's the key. So MFCC is this, right? Log of this S delta K, okay? Doing another IDFT, but in this case, usually people implement it using cosine transformation because they're real part, okay? So the real part of the real Castro, we can directly use this cosine to compute, okay? So don't do DFT. So the log of S, and this S delta essentially is output from this triangle, the energy output from this triangle filter. So you get speed signal, look at them in the frequency domain, and then you design this set of triangle filters equally spaced in MEL scale, has equal bandwidth in MEL scale. Okay. Then you look at your signal as they are going through these filters, they have this energy output. You take the log of those energy output, then you do a Castro analysis, which is basically multiplied by another transformation. Then you get the MFCC values. Okay, that's the derivations of MFCC, right? Think about the process, right? Doing the spectral representation, then go through triangle filter. They get a set of points. Those are energy output from those triangle filters. Then one of those triangle filters, then you say, okay, let's do a Castro now. So in LPCC, what does it do? It says, okay, go to spectral, okay, then do LPC analysis, get a set of coefficient, okay, and then you take the transformation into a Castro analysis. Here you say, let's get the spectrum, and then go through a set of triangle filter, look at the energy output from those triangle filter, and then go through the log and Castro transformation. Okay, so think about the difference between LPCC and MFCC is the way we represent the spectrum, right? So in LPCC, we have speed signal in a spectrum, and then we do linear prediction analysis, getting those alpha coefficient. It provides a smooth curve in a speed spectrum. Then you do Castle analysis to clean it up. Okay. In MFCC, you say, okay, let's take speed signal and has source and filter all combined, right? And then going to the spectrum, and then it goes through a set of triangle filter and look at the energy output of those triangle filters. Then you do Castle analysis. So the real difference between LPCC and MFCC are the way we represent the spectrum. Okay. In LPCC, we represent the spectrum using linear prediction coefficients. In MFCC, we represent the spectrum using a weighted triangle energy output. Then utilize that as an input to the Castle analysis. So these are mathematically that's the only thing that difference between the two. Okay. Conceptually, the difference is one is derived based on vocal tract resonant frequencies and stuff like that. Okay. MFCC says, okay, we want to represent. We're carefully designing all these triangle filters because they look like our hearing membrane. Okay, it looks like our amplitude movement. Okay, and because each of the membrane has this amplitude movement that's intertwined with the trained nerves that creates energy within them. Okay, so we adds up the energy within each of the bandpass filters. So it's an inspiration from a hearing. So it's inspiration from the hearing mechanism, such that we design all those triangle filters in the nail scale. Okay. LPCC are inspiration from the vocal tract. It's like a connected tube, water bottle, creating resonance. So you have pole location as a format. Okay, so utilize those as a approximation to derive the feature. So the difference really comes down to here. Okay, so let's look at the practical implementation here. We know we never do an actual Fourier transform. Do some version of EFT, right? So it's sampling a frequency domain. So what we need to do is actually find the DFT bins correspond to the desired frequencies. Okay. Okay, so there are different ways change from linear to male scale, right? Say if you're interested in picking 20 male component covering 0 to 5 kilohertz, right? So say you might have 0 to 5 kilohertz, you want to design 20 male filters because you have a 20 male scale. Okay, and each one is a center frequency scale, male 1, male 2, male 3, male 4. Okay, now I need to know male 1 correspond to which of the DFT beats in my actual linear frequency, because we're not getting a continuous frequency representation. We're getting a discrete frequency representation because 512 at FFT means you're breaking 2 pi circle into 512 points. Right, so every single point corresponds to a discrete set of frequency, not a continuous set of frequency. Okay, so you take components from one approach, say take components from 0 to 1 kilohertz, make them linearly equally spaced. And next 10 components to be log distributed. Okay, so for example, you say your endpoint DFT is 10 to 24 points, your FS is sampling rate is 10 kilohertz. Your resolution is 5,000 divided by 512. Sorry, it should be 512. So every frequency beats, okay, they correspond to 9.6765 hertz. Okay, right. The first frequency beats is 9.765. The second is 19 point something, right? So you find the closest K, okay, that corresponds to the frequency that you want to do. Okay, so in the male scale, say less than 1,000 hertz, if you want 10 ohm, for example, then that means every 100 hertz you need to have a center frequency. That 100 hertz, you'll find the DFT bins that correspond closest to 100 hertz, which is probably the 10th bin, right? The 10th bin will be 90 something, right? So that will be probably close 10 or 11. Okay, so again, you don't hit the exact 100 hertz. You find the closest DFT pin that actually correspond to the male scale that you actually design. Okay, so there are a lot of approximation happening here. Just keep in mind, in reality, in implementation, also I want to keep in mind, every toolbox you use, their MFCC computation is always a little bit different. Okay, so stick to one toolbox if you want to do cross things, right? So if you say I use a particular toolbox to compute MCC here, and then build a system, and tell other people to repeat your system, make sure they use the same toolbox to compute the MCCs, because the way to compute MCCs, there are always subtle differences that people utilize. So keep that in mind. Okay. All right, and another thing is like law of total energy in the bandpass fashion, right? It's close to the idea to the psychoacoustic evidence. So each critical band, right, has a frequency response. If I band corresponds to I critical band, the center frequency, okay, FCI equals to K Fs divided by N, right? The kth one, Fs divided by N, that's just the frequency bit differences, right? The kth one is just that kth one. Okay. Now we can say H of E to J omega, okay, the frequency response of that filter, usually we write it as a triangle filter. So we can calculate the total log energy, okay, this is triangle filter, log energy multiplied by the triangle filter, and then sum it up to get all the white base. Then you zero all other case. So your CS7 essentially is 1 over nk from 0 to n minus 1 yk into jk2 by n. So again, just need to design this triangle filters, right? So if you have 5,000 hertz, say you want to break them into 26 mel filters, you can say that's how do I break them into 26 mel filters, and say, okay, utilizing maybe, okay, less than 1,000 hertz, they are equally spaced, okay, in terms of linear and mel. And here they are log relationship, or you just follow the equation that we write log 2 and that kind of thing. You want to find this center frequency in the mel, and then look at the DFT speeds, okay, and then in the original frequency linear scale, say okay, that DFT being closest to the mel filter center frequency. That mel filter has this bandpass filter corresponding. So let's say maybe this is 25,000 hertz. This is to 4,500 hertz, and look at the corresponding DFT beams. Okay, then you do a triangle weighting. Okay, all the frequency component within that filter, sum up the energy that you get from it here. Okay, then you repeat for all of it. Then you do log and you do visual analysis. So that's the usual approach. So for integration, we just need to decide, okay, how many filters you want here, and how many filters to split what range of the frequency. Okay, here they say 5,000 probably because their sampling rate is 10K. Okay, if you have 16K, you're splitting this into splitting 8 kilohertz into say 26 or 30 filter mel filters, or if you're even higher, okay, 32, 22.1, 44.1 kilohertz sampling rate, then you're splitting even a wider range to a finite set of triangle filter. But idea is, again, simple. You think about how many filters you want to design in now. Okay, they will all equally spaced in terms of center frequency. They will have the same bandpass width. Okay, in mel scale. Okay. Now in computation MCC, what you do is do DFTs. Okay. Now you represent your switching on your spectrum. Okay. You know this point is correspond to a particular frequency. You know this width corresponds to a certain frequency. And you find the closest DFT beats that correspond to your design of triangle filters, and then look into the DFTs that you had just computed. Look at those range. Look at those values. Take the energy weighted by this thing, right? So again, sum of the energy and weighted by this triangle filter. The values multiplied by the triangle filter. Sum up the energy, give you a number. Sum up the energy, give you a number. Okay. So then you effectively have all these numbers. Then you do this e to j divided by n times n. Okay. So because of the spectral symmetry, okay, and a signal of interest is real, usually people will replace the inverse DFT, the actual definition of captron with DCT, Fourier cosine transform. Okay, they will give you the same thing. Okay, because of the signal of interest is real. Okay, so you can do cosine transform instead of IDFT. And this is the reason why it's back in the day, this is easier to implement as a signal processing device. Okay, because generating cosine waveform is easy. Okay? So generating things that have, imaginary part and recompute that's tend to be very more tedious, okay? But if you have a real circuit generating a cosine oscillating waves and multiply by the signal, you just go through some filter and sum it up. Okay? This is a very easy circuit to run. So you can do cosine transformation and they also speed up the entire MFCC computation. Okay, so that's more of a computational issue. Mathematically, they're equivalent because the signal of interest is real. Okay, so again, I want to repeat computational MFCC exactly the same as LPCC. So you have to decide short time, windowing, all those things are the same. Once you get a catch-up coefficient, you still do dynamic spectral, the velocity, the acceleration feature, you still compute. All those things remain the same. The only thing that really difference is this is basically how we represent the features. Okay. So LPCC and FCC, let me do a little bit of a recap. They are very useful set of coefficients, or we call them numbers, okay, to compactly describe the speech sound. Okay. Usually they largely focus on the vocal tract characteristics. And I think this is important. Okay, you can imagine all the things that we've done, right? If you think not from the science perspective, it's more from an engineering perspective, which is quite interesting, where you actually eventually using a finite set of coefficients, like 13, 30 maybe, to fully represent a segment of Windows that time waveform. And it captures all relevant information that you need for the speech text, right? So you can also imagine this is a compact representation of the speech sound that you have. Okay, so it's efficient. Okay, just a few coefficients that you need. Okay, you don't need to store everything else. The rest of them are being thrown away. You don't have to compute them. All you need to do is compute this set of coefficients and compactly represent the useful information that exists in the speech signal for whatever relevant risk you actually wanted to do. Okay. So this coefficient a lot of times used as front end for many speech technology. Okay, so automatic speech recognition, you use MFCCs. Automatic speaker recognition, use MFCC. Okay. A lot of sound event, okay, you use MFCC to do computation. Anything now across speech signal, you always start by doing MFCC. Okay. Even at some point, we always joke, right? Even anything, as long as the price is very small, you can use MFCC to compute. The real reason is I've seen people do MFCC on non-speech signal, and it still works, okay, but there's no speech production, source and filter kind of thing that's happening there. So eventually what's happening? So you can think about MFCC, we inspire everything from speech signal, okay, speech production, speech perception, then pass filter. But what in reality, if you don't learn anything about that, you just learn this, okay, what does this operation tells you? It tells you I'll give a good granularity to low frequency, give a higher granularity to high frequency within my signal. If for any signal that has this property where a lot of information that exists in the low frequency and the difference between them, we need to be very sensitive, but a high frequency variation we are less worried about, okay? Then any of those signals you can compute MFCC. It'll give you a very good representation, okay? Because and why it works is in real life or in physical world, okay? Many of the physical systems or biological systems, okay, we are low frequency systems, okay. A lot of high frequency things that happen in our life, they're either transient or things just get washed out. They're not really meaningful, okay, just a few jumps here and there, okay. Those are high frequency. You need to be aware, but they don't make a huge difference, okay. So in speech sound, it's the same thing, okay. Get rid of all these things, you can still hear what people say. Get rid of these things, you don't know what people are saying. Okay, so a lot of those low frequency things in real world, physical world is important. That's why MFCC itself works so well. Okay, I think mainly because of that. Okay? And it works better than LPC is I think it's because it actually LPC is a way too rough of an approximation. It gives you that spectral envelope of kids. Okay? But here, you still get the actual sort of granular representation at a very detailed frequency spins here. Okay, and the LPC is kind of an overall shape optimization. Okay, MFCC really looks at individual sort of parts, but I don't want to have too many bits here. I want to have more bits here, but the fewer bits here. And this kind of representation helps in modeling a lot of the real life signal, especially discrete signal. So just keep that in mind, as an engineer, we design all these tools with inspiration, okay? But if you stand up, okay, from an abstraction point of view, from a mathematical point of view, it's just a set of operation that tells you, okay, I'll give a lot more sensitivity to low frequency and less sensitivity to high frequency. Okay, once I give it to that, okay, I use another transformation, okay, to re-represent the thing here, okay, in terms of a capture analysis. So again, capture analysis is basically another way, okay, to recompactly represent already compactly represented things here. Okay, so DCT is another transformation that people, if you're in a domain not in this domain, not in speech domain, not in capture domain, if you look at image processing, okay, JPEG is an image encoding method. Okay, it uses discrete cosine transform. Okay, so again, you can also imagine discrete cosine transform. It's just a set of compression. Okay, so if you think about that way, the MFCC process is saying give sensitivity to low frequency, give some crude representation of high frequency, and compress it. And then you get MFCC. Okay, so that's another way to interpret this set of coefficient. I think either way is okay, but down to earth is people in speech technology find this MFCC coefficient very good. Okay, to do all sorts of stuff. Okay, baby sound crying, all these things. You can use MFCC. Anything that's human generated sound, use MFCC as your starting point. It won't disappoint. Usually gives you a fairly good accuracy to start. Okay. Okay, so take home message from this section. Okay, scientific evidence that we know human hearing perception. I want you guys to understand human hearing is you can imagine engineering approximately as a bandpass filter in your ear. Really understanding perceptual scale. Okay, that key part is important. Okay, the way we humans listen to the signal is not the way that signal presents itself. It's also not the way that the other person speaks. Okay, it's in your brain, your ear, how it processes it. It's not exactly one-to-one mapping to the other person. So this difference is it's important. Okay, to always keep in mind. Okay, it's not the speech sound directly represent the perceptual scale. And then when we understand something, we always want to understand: is it something about how we generating that speech sound, or generating that signal, or is it the way we perceive that signal? Okay, these two tend to be different. Okay, we have to understand that. So scientific evidence and bandpass filter is an engineering approximation to our hearing. Bark scale, Mel scale, they are not the same as linear scale. This is the most famous perceptual scale. There are other perceptual scale, yes, okay, but these two are the one of the most famous ones. Mel scale is because Bark scale is one of the first perceptual scale people start to realize, okay, hey, people think loudness is energy is the same, but loudness is different. Why? Then it's because of the Bark scale, the critical evidence. Because of this idea, right? There are lots of scientific knowledge that people derive about using impression algorithm. Why? Because it's perceptually, if you can perceive and don't perceive, okay, that means there are ways we can design our algorithm to save on stuff, right? So for example, like the way I say it here, right? You can also imagine MFCC, the process of compression. That means if I do MFCC, it means I'll put a lot more bits in the low frequency, but high frequency I put lower bit. So I don't need to have as many bits to represent the full speech signal, so that you can still hear very better. Okay, so can imagine the way we can think about how we human perceive this patient. Engineers will leverage that. So because there's something you can't hear anyways, we don't need additional storage to store those things. So we can compress it, or later on people they will even hide message in a particular way that even you don't hear it. Okay, but that's okay. It's still message will still go through that. It's more of a military sort of thing, right? So yeah, perceptual scale is a perceptual understanding of human speech, plays a major role in the speech compression, saving bits, saving memory, saving computational cost, saving transmission cost. Because we know your ear only responds certainly to a certain set of frequency, and that's all it matters. The rest of them you don't care, so you might as well get rid of them so that you can make things faster, more efficient, and so on and so forth. Okay, so you always need to think about this thing, right? So the thing you hear anywhere, they're really never the same thing. Okay, I think I've said this right. People now worry about fake audio, fake thing, right? So in reality, everything you hear is not a real one. It's always some distorted version of the original produced version, right? So that's why we know human itself, we are also be deceived because our perceptual mechanism will tell us something about the things that exist in the signal, okay, that may not actually exist, or you may not actually tune toward those specific frequency. Okay, so these are certain things you'll be aware. So everything is always a distorted version of something else. Okay, so as engineer, you just need to worry. Okay, the signal, the recording here, what best represents this thing for the technology that we provide. That's important. All right, so I'll do let's wrap up the MFCC part, the speech analysis. I'll start to do a little bit intro on the ASR, the learning part, the speech recognition part. And we'll continue going on to more detail and some brief overview next time. Okay, so we know this, right? Throughout all these past couple of weeks, we'll stop at this point. Okay, we'll cover the rest of it in the next level. So the speech signal, it goes through we call a front end signal processor. Okay, we call them feature extractor. It can be MCC, it can be LPCC. And we turn those things as acoustic features per frame. Okay, then ASR system basically involves additional thing we call the pattern matching. Okay, so we know the very first beginning of the class, right? So every speech signal can be written, word can be written as phonetic transcription. Every phonetic transcription has a corresponding pronunciation. Okay, so what we need to do is basically looking at these acoustic features. Okay, finding out this set of acoustic features correspond to a particular pronunciation. Now, through that pronunciation, then we say, okay, because of this set of pronunciation, we call phonetic transcription, that becomes this set of words. So the pattern matching is trying to match the acoustic features to the set of phonetic symbols, okay, phonetic descriptions of our sound. And so if we can match that, then we're able to recognize the speech, meaning taking the speech signal into symbolic word transcription. Okay, and this pattern matching involves actually two sets of models. Okay, one model we call acoustic models. Okay, we'll talk a lot about this. Acoustic models say, okay, how do I find a model that actually can take a sequence of acoustic features and then tell me these are a sequence of phonetic transcription. Okay, that's an acoustic model. With a dictionary, that phonetic transcription can be a transcription of word, but then there's an additional model we call language model. The language model will further, it doesn't depend on acoustics. It has nothing to do with the sound. It only depends on the grammar, the probability of the word sequence in any language. It has nothing to do with acoustics. Okay, the acoustic model tells you from these acoustic features what the most likely sequence of symbolic words. But maybe that symbolic word with noise, with your errors in your acoustic model, you may be wrong. Okay, maybe you have say she want, she I want. Okay, you shouldn't have an I there, okay, because in any language or English, you don't have these two subject verb, two subject nouns at the beginning of the sentences. Okay, that will have a very low probability. Okay, so you have a language model that can rescore all these word sequences to make sure you generate the most possible word sequences, okay, of a particular language. Okay, that's what we call the language model. The language model is usually trained separately on the different texts, okay, purely on the word. So this is more like an NLP, natural language processing type of problem. But we'll also touch upon a little bit in the context of ASR. Okay. This will spend quite a bit of time to talk about how to be actually the sequence of acoustic features, and then trying to learn the model and what that model is, and then try to output a sequence of those simple sequences. And finally, once after this, then you have a recognized strings or recognized task. So you have taking about a speech signal to the recognized strings. Okay. So the front-end processing signal is performed frame by frame. Attempt to characterize the most informative speech signal within short duration. Pattern matchers, or called machine learning or learner, attempts to align input acoustic feature with a template or model of candidate words or some subsequences to choose the best match among them. Okay, so you can imagine automatic speech recognition system is just a process of picking the most likely sequence of words, okay, given acoustic sound. Okay, so there are many kinds of pattern matcher. Okay, the one that actually works quite well and then actually evolved until today we call the statistical pattern recognizer. Okay, so that means the pattern recognizer are actually derived from large amount of data by computing certain statistics. Okay, and then in today nowadays modern era we call that machine learning. Okay, in the previous day they called it statistical pattern recognizer. Okay, they are the same thing. They are the same thing. Basically, gathering enough data, estimating a model parameter using statistics. Okay, then once you have this, you can start using it to do inference and then try to find what's the most probable things. So statistical pattern recognizer is a probability-based pattern recognizer. Okay, it's trying to find the most likely. So it's a probability-based approach in terms of trying to do recognition. In this approach favors a selection of word family with the highest probability of matching the input sequences. Okay, and highest probability is the key word here. Okay, so this kind of learning is purely data-driven. Data tells you if you see those features, they are most likely in a set of word sequence. If you see this kind of word sequence, it's likely in this particular language, it should be written this way. Okay? It's always this most likely process. So keep this in mind because what that means is whatever the data is most likely, your system will be that most likely. Okay, so if your data is not correct, okay, or your data has some issues, then your most likely may not be the correct one. Okay, but that's how modern days machine learning hits the same problem. But at that time, it's the same thing. Okay, so it's a data-driven, most likely way of doing a pattern recognition. Okay. So again, basically I did a simple thing. So I said, say you have three vowels you isolated. Okay, you do recognition experiments or one of the three, right? So three-way classification. So OT is a speech spectral features, and a friend can be LPCC, can be MFCC, right? Lambda I is a model of each vowel. So R has a model, E has a model, U has a model, and we'll talk about what that means. Okay. So you can do a pattern recognizer by saying, okay, find a model that give me the highest probability. The model I given the observation. Okay, given I've seen this observation, what's the probability of that model? Give me the one that's the highest. If that's the highest, I'll decide this. Then I finish my recognition experiment. Okay, so yeah, I want to go through these details because I want to make sure this logic is clear. Okay, so we're doing a pattern recognizer, a statistical base, that means learning from data. A statistical base also means is actually implementing particular equation to do recognition. It's this equation. Okay, this equation. Finding the set of model. Out of all those models, pick the ith model that give me the largest posterior probability of number I given I have seen observation, right? So this conditional probability, understanding that I have seen observation, all of this model I will compute their probability and then give me the one that's highest. Okay, just keep this in mind. Will eventually tell us how we actually implement this equation, okay, in our ASR system. Now everybody knows Bayes rule. Okay. Probability of in the model given observation equals to probability of observation given model times the probability of that model. Okay, divided by probability of observation. Okay. You have OT given lambda I, so probability of observing a feature sequence OT given a word model. Okay. This thing we call acoustic model. Okay. So if you have this model, what's the probability you'll see the set of features that you see? Those things that we call the acoustic model. So you can build acoustic model for each of the actual symbol or word sequence or word that you want to try to recognize. For each of the word, okay, you can try to build a model and then we can compute the probability of, if it's truly that model, what's your probability of seeing this observation? And go through all the models, compute all those observations. P of lambda I called a priori probability. Okay, basically it doesn't depend on observation. Okay, it just depends on whether this particular model would happen more likely or less likely. Okay, in the context of the ASR, right? If this is a word, the probability of that particular word happen more likely or less likely, right? So it's a prior distribution on a particular word. So for example, this kind of words that always happen. Okay, it's always in the sentences. Okay, very difficult word like things like very complex terminology. Those words don't happen a lot. Okay, those prior probability will be very low. Okay, it doesn't depend on observation. It doesn't depend on the signal. It depends on just generally how likely that word will appear in a particular language. We call it a Fourier probability. Probability of the following word occurs in this particular universe. And this thing we usually say this is a language model. Okay, this is a language model. So acoustic model, language model. So having an acoustic model, having a language model, P of OT, okay, for all the i's, for different model, lambda I, P of OT is the same. So you don't have to actually compute this. So to be able to find which lambda I, which I gives you the largest value, because for all the I, they are all the same. So all we need to do compute is this thing, okay, which is the acoustic model and the language model. Okay, so well later, basically, this is a implementation of an ASR. Well, later tells people what are some of the key things to actually be able to learn this. What's the option? When I say R, what's the probability mean seeing this MFCC? When I say U, what's the probability seeing this MFCC? And again, we cannot list out all the probabilities like a table, right? You cannot say R and I look at all the MFCC and this MFCC has this probability. No. So eventually we need to have a model, a parameterized version of this probability distribution. Right, so we know this is again a probability distribution, and people probably recall probability, right? So you parameterize, okay, your probability distribution so that Gaussian distribution only has two parameters. So you only need to estimate two parameters before then you can fully compute any probability if it is Gaussian distribution. Okay, so in speech here we'll talk about another model that also has a set of coefficients, a set of parameters. You just need to estimate those parameters. Once you estimate, you can actually compute this probability. It's called parameterized acoustic model. So you cannot list out all the probabilities. So you have to parameterize. You have to say, okay, I assume my speech sequence is a particular model of some sort of parameters that follows that kind of formula and give me a PDF. Okay, so the PDF has parameters. Now you need to take data and estimate those parameters. Then once you estimate those parameters, you can compute this paper. As well, we'll take you guys step by step through that approach. Again, same thing with the probability of lambda I. We can assume each of the word, okay, is probably the word sequence probably follows a particular probability distribution. Okay, then we can estimate those probability distribution, and that probability distribution will have parameters, right? And just estimate those parameters. And so this language model, you know this well, okay, it is the same, but the cruder version of what you see nowadays in ChatGPT. That language model, these two language models is the same terminology. Okay, just that language model, like a large language model, has a lot more data. The parameters that they use to represent P of lambda I is more complex. They use a deep learning transformer structure. Okay. But in language, in here, we'll use a simplified version of P of lambda I, but they are the same. P of lambda I basically trying to give you the most likely word sequence. So large language model nowadays, when you see those challenges, it also gives you the most likely word sequence. Okay, as it responding to you. Okay, so back in the days in the automatic speech recognition, we've already utilized that kind of concept in trying to make sure our speech recognition system also works here. Okay. Okay, so once we cover all those things, then you can implement this equation. So our mass speech recognition essentially is the R max over all the models. Okay. And lambda I, it has to be a finite set of models because you have to look through all the models, right? Look through all the models to find their own probability. And that's where the knowledge of the linguistic comes in. We know, right, in English, there's only 40 forms. Right? So if you want to build a model, a form, you only have 40 models to build. So which is reasonable, you can do that, right? So this particular implementation relies on a discretized set of units, okay, that we can formulate within a particular language, so that we can say out of all the finite set of lambda I, I'm going to pick up I such that posterior probability is the largest. How do I compute posterior probability is largest? I need to compute their acoustic model probability. Okay. I will compute their a priori language model probability, and these two things put it together, and I get this posterior probability. The one that's large, and we're done. Okay, so there are a lot of details around this, but this is the general concept. Okay, in terms of doing speech recognition system. Nowadays, it's still pretty much the same thing. We have a more complex listing. Okay, even to the state of the art, what people do is say, okay, I don't want to have two probability due to this. We can add to them a single probability. That's another story. But it still follows very similar idea. It's acoustic model, language model put together to the posterior. Okay, keep this in mind. We'll start moving into this particular. So in terms of the course structure, right? So before here, a lot of these are processing filters, transformations, Fourier transform, Z transform, Capstone transform, and so on and so forth. Okay, starting from here to this point, it's all probability. Everything is probability and statistics. Okay, how do I compute this probability? How do I compute that probability? Okay, how do I do estimation? Okay, everything is probability and statistics after this point. Okay, so ASR, like I said at the very beginning of the class, is a process of combining all the basic core mathematical courses that one has taken as undergrad, put it together. That's our mass speech recognition. 好，我们今天先上到这边，我们接下来就开始往这个几率。如果大家对几率比较熟，应该就开始看起来比较顺眼那样。如果大家是对几率比较不熟，就会觉得那就是另外一件事情。我知道后面是都是几率跟统计。